He leads multidisciplinary work in the areas of data infrastructure, data science, and algorithms towards contributing to the understanding of neurodegeneration in the aging brain. Prior to CBR, he held R&D positions at Lucent Technologies, Bell Laboratories, Ericsson in Silicon Valley, and in AI-focused startups in language translation and financial information, and Oracle, working on both systems and algorithms for signal processing, communications, networking, cloud technologies, and ML and AI. Today, Chini is going to be talking about towards advanced detection of cognitive impairment in India, data and AI at the Center for Brain Research. To give you all a short abstract for today's talk, the Indian populace is expected to have, one second, the Indian populace is expected to have a 60 plus demographic of nearly 300 million in the next decade or so, and faces a growing dementia epidemic amid large gaps in healthcare infrastructure, awareness, early detection, trained personnel, and public health support. Varied ethnicity combined with risk factors and co-morbidities such as metabolic and cardiovascular conditions. The Center for Brain Research is engaged in an effort to identify a set of biomarkers that are relevant to India to aid the advanced detection and prediction of the pre-dementia stage of MCI, which is mild cognitive impairment. This necessitates a strong computational component based on multimodal data and algorithmic advances in statistics, ML, AI, and signal processing. Chini's talk today will provide an overview of the ongoing work at CBR in the areas of data and AI. Over to you, Chini.
Thanks, Nonil. Thank you, CDPG folks, for inviting me to represent CBR here and give a little bit of an idea of the kind of work we do here at CBR and its purpose for why we are at IISc. So here are a couple of things, right? When we talk about this kind of a problem, it's interesting. I'm an engineer by training, but here I am at a lab that is working, trying to understand something about cognitive impairment in humans as a whole. And so the questions come forward, right? What is the problem? Why are we talking about India in particular here, as the title says? Then how are we going to address this problem? It's not going to be it requires a multidisciplinary approach. And then the question of when, obviously depends upon when we figure out how, and then we will get an idea of when. So what I will do today is focus more on the why and the what of the problem, because the problem is very complex. It's not an easily solvable one. And as we go through some of the material I've prepared, I hope you will be able to see why. And as we conclude more towards the end of the of today's presentation, I'll open up some. I'll basically start posing questions and challenges that the effort to address this problem faces, right? So suffice it to say for now that this is not a solved problem, far be from it. So we have a big problem on our hands. We have a very important problem on our hands, let's dive right into it. One quick question, Namrata and Novanil, would you prefer that I take questions towards the end, or do you want to make this interactive? Will you kind of moderate it? I'll leave it to you.
If there are any questions in between, I suppose participants can raise their hands, but we'll keep them very short during the talk, and we can take longer form questions towards the end.
Sounds good. Thank you. All right. So let's dive right into it. I don't know how many people in the audience know something about CBR. The Center for Brain Research is a non-for-profit society And you're probably familiar with the name Chris Gopalakrishnan. He is one of the co-founders of Infosys, a rich man with serious vision and altruistic tendencies, which is brilliant. And CBR owes its existence to Chris's largesse, started by his by generous funding from Pratiksha Trust and run by Sudha and Chris Gopalakrishnan. So CBR has been around since 2014. Actually, the foundation stone was laid in 2015, and we now have a new building, and we are housed on the campus of the Indian Institute of Science in Bangalore. We are just separated by one building from CDPG, so we get to see our CDPG buddies almost on a daily basis, practically on demand, which is great because the collaboration is really quite something. And just to acknowledge many of our donors and supporters up front, there is the Indian Institute of Science, of course, who's hosting us, the Tata Trust, the Department of Biotechnology, the Government of India, Gates Ventures, and the Alzheimer's Association are all some of our key supporters. So with that acknowledgement, let's go forward. So here is a picture, a couple of pictures that talks about the pathology of particularly Alzheimer's, which is also called amnestic dementia. So if you look at the left picture here, I hope you can see the the laser pointer moving around. So on the left half of this plane is pun for all of you who are versed in control theory. This is stable. The neurons are in good shape. But on the right half of this plane, are where the deteriorating neurons are. So why does this happen? It happens due to a bunch of misfolded proteins, and they lead to what are called plaques and tangles. So the plaques basically almost seem to function like very powerful resistors between neurons and impede the flow of the bioelectrical current that keeps the brain humming. And obviously what happens is when neurons are impeded from functioning, over time they will atrophy and that part of the brain can die, basically, right? And so this is basically the pathology of what causes Alzheimer's. And where are we going to find these proteins? Obviously, if you are talking about the brain, the first thing that comes to mind is the cerebrospinal fluid, but that's obviously very hard to get. And so one would hope that you could measure something in the blood plasma. Okay, so that is about the proteomic pathology of Alzheimer's in this case. So that's it. So why am I talking about this? Because the mission of CBR as a mission-focused research lab on IISc campus is to develop a composite biomarker for the detection of the early onset of dementia. Okay, and if we are able to develop this composite biomarker, we would hopefully be able to detect things in advance or even predict the potential onset of what is a stage called mild cognitive impairment. We will get to that in a moment. And using this, we hope to be able to help the healthcare community design interventions that can either arrest or prevent or postpone dementia into late life, where the impact on the person as well as on their near and dear is not as bad as it would be if somebody were to develop this earlier in life, right? So here is what Navneil was alluding to in the abstract of the talk. So the Indian populace, if we look at the demographics, in 2031 we are going to have close to 200 million. By 2050 we will have nearly 320 million. This is roughly 320 million is roughly the population of the entire United States, right? So you can imagine how big of a burden we would have if even a small number of the 60 plus, 60 years plus people were to develop some kind of dementia. Can you just hold for a moment, please? This is unexpected. Okay, all right. So the chart on the right is a rough sketch, is a conceptual sketch of how brain aging happens. Excuse me. Yeah, so the sketch basically shows two curves, right? The curve on top says how a normal functioning brain would degenerate gracefully over time, but the other one below it shows that, in some people, the rate of degradation can be a little faster because the slope of, as indicated by the slope of the curve. And there is the stage which is called mild cognitive impairment. And past that, the degradation can be much faster, and that's where it descends into dementia. So this knee of the curve, which is MCI, is basically before that is where we should catch things if we can. Okay, because that is where interventions will help. But after that, it's almost hard to do anything. So what we want to do then is this tells you why we should do aging brain research, particularly particularly in the Indian context because of the population setting, right? So let's take a look back again. So let me go back to the proteome, to the brain picture and the proteomics thing that I was talking about a couple of slides ago. So there has been a lot of research in the bioscience community where people have been trying to find the most indicative markers of what may indicate for Alzheimer's. So right now, the most powerful marker or the most definitive marker seems to be this protein called p-tau for phosphorylated tau. And there are many p-tau proteins, out of them p-tau 217. And if you look at the leftmost curve in this chart, that tells you that p-tau 217 is by far the most indicative biomarker, but very importantly, it also indicates something a little scarier. The the biochemical processes in the body that basically start, lead to the onset of cognitive impairment and potentially one of the family of dementias can start as much as 25, more than 20 years prior to the actual manifestation of symptoms. So today, we only know that somebody has Alzheimer's or somebody has Parkinson's when you see symptoms, but things can start 15 to 20 years before. So can we find markers that we can catch many years before and predict something or detect in advance? So in a sense, we are trying to do what a cardiovascular surgeon would do for you today. They would take a look at some of your reports, maybe over time, and say, well, you're beginning to see an increase in cholesterol or lipids, and this can lead to heart disease because it's getting to dangerous zones. So you better start eating right, you better start exercising right. So those are the kinds of interventions. Now, it took a long time for even those biomarkers for cardiology to be actually created. Apparently, over the course of at least 2 to 3 decades, over a very well-known cohort study called the Framingham cohort that happened in Massachusetts in the US. So essentially, where cardiology was maybe 40, 50 years ago, this science is there at that stage today, right? But we have to do this sooner rather than later so that we can prevent we can help with quality of life for as many people as we can. So the disease process gestation basically exceeds 15 years, and we would like to find out when it starts and how quickly can we detect it and basically predict it if we can. So how can we approach this problem? Let's start from the right. So there is the patient on the left, but what we can do is we can gather data from longitudinal cohorts in India. Longitudinal means you observe the same person or same group of people over multiple years. So what you get is a time series of data, right? And this data and samples is got to be supported by a lot of basic science research of the kind that we referred to in the previous chart, where there were all these protein concentration charts. And along with that, we also would need to do some other manifestation related observations. So if you look at this box that says by potential biomarkers, I should say potential biomarkers, they can be in proteins, they can be genetic, and their manifestations can show up in neuroimaging, it can show up in vision problems, auditory problems, essentially sensory problems, right? Speech, gait, and then also if we can measure something in the electrical activity of the brain using things like EEG, and do a whole bunch of data analysis, standardization, validation, and maybe if any detect any target molecules or drugs or even interventions, may have to go through clinical trials, and then you go to a translation activity, and then you feed it back into the clinical community that can deal with their patients, right? Or there's subjects who may have this gnawing feeling that they or their near and dear are beginning to show some signs. So they take them to a neurologist and get them go through a series of tests and such. So what do we do in CBR? I just mentioned longitudinal cohorts, so that's what we do. But you also saw multimodal assessments in there. So here are the things we do in CBR, right? So there are a bunch of harmonized assessments, which are basically fundamental to everybody. We do a clinical evaluation, we do cognitive assessments, because obviously, that is the most direct indicator of whether somebody is cognitively healthy or not. And then we can take their blood samples, do blood biochemistry, etc. That can lead to proteomics, genomics. And then we can do a whole bunch of measurements that basically indicate their current level of functioning, right? That includes everything from brain imaging, optical, high resolution imaging of the retina, and so on, cardiovascular, gait and balance, audiometry. We have talked about all of this, right? And by the way, it is not just biological issues. There are a whole bunch of socio-demographic issues which affect people, their social network. Are they undergoing stress in their personal or professional lives? Do they have enough to eat? Do they have enough to eat of the right kind of food? Are they living in areas where there may be pollutants that may be harming them and causing changes causing biochemical changes in their body? So there is a whole bunch of stuff that needs to be studied. And in CBR, we run two longitudinal cohorts, an urban cohort called TLSA, Tata Longitudinal Study on Aging, and another rural cohort called SANSCOGS, which is run in an area called Srinivaspura, in Srinivaspura Taluk of Kolar district in Karnataka, which is about 100 something kilometers away from Bangalore. So we observe these two cohorts over time, okay? And you will see some statistics about these cohorts, but let's get quickly to an idea. I'll give you an assessment, and an idea. We talked about some of these in the previous slide. So the core assessments are socio-demographic, clinical, cognitive, and blood biochem. And then there are a whole bunch of specialized assessments we do from their samples and by doing some kind of imaging and signal gathering, if you will. So here is an idea of the and longitudinal overview of the cohorts we have. So in the SANSCOG cohort, in the rural cohort, we have 10,000 people, participants, and all of them have come at least once. Over 6,000 people have been examined twice. And then, of course, in between, when COVID hit, it was not good because the rural cohort started in 2018. So there was a lull in between and there was a gap. So you would see that, there is what seems to be a precipitous drop in the number of people for whom we have more data longitudinally. Correspondingly, in TLSA, it's a little bit better. TLSA is a smaller cohort. Now, here is the interesting part. TLSA is all composed of the participants in the TLSA cohort are all those people who live and work in Bangalore. Unlike the SANSCOC cohort where they all live and work in the rural area. So the genetic makeup, the genetic diversity is much more in the TLSA cohort. And, they are also largely professionals who have had many, many years of schooling and education. So their situation is quite different from the largely agrarian and rural/tribal communities who work in Srinivasapura. So that's why there are two cohorts where we are studying these folks and gathering data from those. The key inclusion criteria here is that when we recruit or when somebody joins a cohort, they have to be cognitively healthy. Okay, they may have other problems, comorbidities in the form of diabetes or kidney disease or what have you, but they have to be cognitively healthy. So over time, it is possible that some of the people we are observing may, begin to exhibit signs of cognitive impairment. And that gives us a small sample of people who in clinical terms, we would call them cases. The rest of them who are normal would be called controls. And then we would do the typical analysis so that we can try and understand why some people are affected more than the others, right? And then here is just a quick picture of the instrumental overview as well. Like I said, we collect, gather data from multiple instrumental sources. But as we go longitudinally, there are fewer and fewer people. Now, here is the thing about instrumental assessments. Things like MRIs and OCTs and all, MRI in particular is not even very practical because it's a big, heavy, noisy, claustrophobic instrument. So you get very few people. First of all, you cannot do an MRI on everybody. That's just hard to do logistically. And among the people who decide to undergo an MRI, not everybody may complete the entire MRI set of sequences we would want to do. So because of the nature of the assessment itself, people may just get up and say, I can't hold on to this. I'm getting up and going away. So we may, with instruments, it is very likely that there will be large gaps in data, but that is the nature of the beast, right? So we have no choice but to deal with gaps and sparse data when it comes to instrumental assessments. So what do we do with all this data, right? Now we come to more of the technology side of things. So I hope by now I've given you an idea of why are we trying to solve this problem in the Indian context. By the way, there was one important point I forgot to mention in there about the Indian context. Things like one may think proteomics, genomics, this is all basic to all humans. So it doesn't matter where people live or not. Well, those are not the only determinants of whether there are issues of dementia or not. In fact, India has a large burden of cardiovascular and diabetic issues, as you know, and those turn out to be potentially significant contributors to dementias. Okay, so the influences here are very different from the influences in the Western world where there is more data. But overall, suffice it to say for now that nowhere on the planet does any research group have an idea of how, when this might happen. There are isolated studies related to just MRIs saying, looking at MRIs, we will detect whether somebody has dementia or not and such. But it's a very fundamentally hard problem to say, I'm going to use all of this, some kind of data and predict something in advance as to whether a person who's being observed by a qualified neurologist has a risk of onset of dementia and what is the probability of that and what may be the potential time to onset. So now we are coming into the mathematical algorithmic aspects of this, right? So how do we deal with this? We have to gather the data and set up the problem. So in CBR, we actually run our own data infrastructure including an HPC system and CPU plus GPU compute. Thanks to CDPG, we are building a data stack that looks like this picture on the left. So data stacks are great. They allow us to do a whole bunch of things. So we get a bunch of raw data, we push it into storage, then it requires a lot of, because we are working all the way from raw data collected in the field, all the way back from there, rather than just, we can't just say, curl or W get this data set from somewhere, right? We just can't do that. We have to collect the entire thing. So what we get is raw data, and that means we also have to go through data curation, data validation, and cleanup processes. And as I said, we already have only a small amount of data. One might think that 12,000 subjects is a lot, but it's not. It is minuscule in the modern scheme of things where we are talking about gazillion data points that feed language models and such, right? So this is really nothing. So we need some sophisticated algorithmic techniques. And at the same time, what little data we have, we just have to treat that extremely preciously so that we can create research-ready data, then run it into analysis algorithms and platforms, and iterate and tune and experiment so that we can progressively, refine our study and then try to find the biomarkers we want to find. So in the AI platform itself, what we would want to do is, we would obviously have to deal with the multimodality and of data security, because there is some PII involved here. And clearly we need to do enhanced searches. We need to find, we would also like to do usage patterns for quick retrieval of data, because we would need to be able to slice and dice data. And, over time, we would also want to develop more sophisticated models that may make use of more agentic methods towards, our goal of trying to develop a predictive or a set of predictive models, if you will, right? So with that kind of a, dipping the toes into the data waters, let's go further here. So what are the main questions we would want to ask then from the data set we would have? One, we can say, the population scale question is, how do we model the disease processes? We saw that disease processes can take well over a couple of decades to evolve. Let me throw a hard question here. How do we know whether the protein accumulation in the brain that is typically highly correlated with the prevalence of, say, Alzheimer's, how do we know whether those proteins were secreted here or up in the brain itself, or secreted elsewhere in the body and then carried through? Do we know whether it's just an accumulation of the protein quantity over time, or is there some other biochemical process that suddenly manifests, some kind of a chaotic system or something that suddenly manifests itself in the unforeseen explosive generation or creation synthesis of these proteins, and that leads to a very quick excess at a very ramped up rate? We don't know. We don't have the answers to all of those questions. So we need to be able to do some disease process modeling from longitudinal data, but that also needs to be supported by basic sciences research, which our team of cellular biologists and neuroscientists here in CBR do. So I'm very privileged to be, one of the few engineers working in this big biology lab. Right outside my office is a big wet lab. There are PhD students and postdocs as well here, as well as data scientists and engineers, a small number of engineers, and we are all working together trying to do this kind of stuff. So let us say we do this population scale analysis where we are able to, identify some of these biomarkers, okay, from a large number of the candidates we have. Then our objective is over time to take this towards individual scale. So you train a model and you've generated all these biomarkers in the population scale, but now you would have to say, can I apply this to an individual? Just like a cardiologist can look at your blood and triglyceride lipid profile and all of that. Can we do something where we look at a small amount of maybe 2 years worth of data from, can a clinician look at maybe 2 years of data from a potential patient and apply this model and say, you know what, your risk of onset is so and so, and here is your potential time to onset. Or, you know what, the model doesn't show much for you. So I would not be worried too much, but I would do a few things just to make sure that things don't degenerate at a later stage, but come back next year to me anyway. But in the meantime, do all of these things, right? So we have population scale questions, we have individual scale questions. So how do we do this, right? The moment we say advanced detection and prediction, you have to do this algorithmically. You can't do this, biology can tell you something. The biological, the basic sciences research are essential. Without that, we cannot model disease processes. But you would need to take them in, and then you would have to develop these, apply algorithmic techniques to develop these kinds of, models that can help us. So what are the challenges we face? Well, some of these we already talked about, but let me reiterate. One is the quality of the data. We need scientifically guided pipelines to transform raw data into research-ready data, right? Well, there is the issue of sparsity. We may be able to get blood samples. We have blood samples for most people, and we maintain our own biobank so that we can isolate plasma and serum and then run them through proteomics, some really high-grade proteomics instruments that we have been recently funded by Gates Foundation for. But there is still a level of sparsity, and this is particularly acute when it comes to the instrumental assessments. So that leads to data quantity problems. And then there is multimodality in the middle of all of these, right? How do we transform, images and waveforms to use with a certain amount of text that we get from cognitive assessments, or how do we combine it with numbers that we get from the other assessments like blood biochemistry, etc. So we have a very large multidimensional problem here. The multimodality leads to multidimensionality. So then we can ask the typical questions that are asked in statistics and information theory, right? What are the most independently influential parameters here? So that is essentially the biomarker question. Are those the only parameters? Are there others, ancillary parameters, so to speak, that may be mediators, that may be moderators? We would have to answer all of these. And what are the best ways for us to maintain all of this data in a way that makes it easy for computational approaches to be applied to this data? So we have a constant problem of databases. Maybe we have to do schema evolutions over time as we learn more and more. So that means we would also have to go to ETL pipelines on the side, right? See, technology here has both is both a core role in the form of algorithms and data science, but also a supporting role in the form of data engineering and data science, right? So that's the beauty of this situation that myself and my fellow engineers and colleagues here, our system scientist type folks are here in, where we are dealing with systems, algorithms, all of these all at once. So what do we have as approaches for algorithmic approaches, options? Well, we could start with unimodal analysis, like proteomics data. Can we map proteomics data to the cognitive scores that we have seen? Because we assess all our subjects cognitively. So then maybe we can find sufficient statistics, or at least a subset of biomarker candidates from a unimodal analysis. But now that's not adequate. So can we basically begin to fuse domains and multimodality? So are there reinforcing biomarkers, or are there conflicting potential biomarkers? How do we handle those? So the quantitatively statable problem in all of these is, what are the right methods to do this? So there are typical good old methods from statistics and mathematical statistics and signal processing, but now there is a new way to handle large amounts of multimodal data. That's called machine learning or transformer models, right? So how can we use these? But it's not enough to just throw something at it and see what sticks, because we need explainability in the process. Otherwise, to what end is this going to serve something, right? It needs to be explainable. It needs to go back to our biologists and cognitive scientists who say, this makes sense, this doesn't. So we go back and iteratively refine these models, and it is a truly multidisciplinary, multi-person, multi-year effort that straddles both computational and pure science, basic science approaches to this problem, right? So that basically almost brings me to the end of my presentation, leaving us maybe about 10, close to 15 to 20 minutes for questions here. So what CBR does, and we welcome collaboration. We have internships. In fact, we just announced, I think, unfortunately, we closed already because we received north of 4,000 applications for the internship, for the C-Brain internship program for 2026. But if you are an engineer or a data scientist or a basic scientist who would like to collaborate with us and contribute to this core problem that we at CBR are trying to solve collaboratively with a bunch of other research institutions and organizations from around the world, please do contact us at that email address, communications@cbr-iisc.ac.in. And what I'll do is, here is a shout out to all our supporters who have helped us in cash and kind over time and continue to do so. Okay. And with that, I just thank you all for listening to me. So please do follow us on our social media and our websites. And I'm open to questions now.
Thank you so much for that talk, Chini. Very, very insightful. I'm going to read out one question that we have in the chat from Deepankar Khasnavish, which is, with all the discussions about AI affecting the mind, is CBR also capturing data in this space so that we can build biomarkers much faster and also explore interventions?
With all the factors influencing AI in which space again? Sorry, Noni.
In general, all the discussions about AI that we're currently having, considering the AI revolution that's going on, is CBR making use of, I'm extrapolating the question here, but is CBR capturing data that will make use of these AI models so that we can build biomarkers much faster and explore interventions using these new LLM models?
Well, data is data, right? I mean, we have to capture the right data for the job at hand. And then we have to find the right models that we can apply to these. But yes, I mean, the family of machine learning and AI approaches to modeling and handling large amounts of data will certainly be applicable here. So when I said, approaches from mathematical statistics or signal processing or whatever, please do remember that those are all the mathematical foundations of modern AI and ML algorithms, right? So by doing those, we are not trying to supplant AI and ML. And I would say sorry if I conveyed that impression by any chance, but no, that's not the intent. But I also do not want to presuppose that we only need a large model for this. Okay. We need just the right model that can make this happen, in the right way in a short amount of time. And do it the right way, most importantly.
Thanks, Srini. Any other questions? I will ask one question, Chini, as we wait for people.
Sure.
We spoke about the multimodal nature of CBR's cohort data, as well as the high dimensionality of the data set. Do you foresee that the number of biomarkers that are being currently evaluated for advanced detection of MCI, do you see those collapsing to a core set as it becomes apparent that more and more of these biomarkers are noise rather than signal? Or do you predict that all of these biomarkers will have some contribution to detection?
So let me clarify the use of my term biomarker here in the first place, Novanil. What we are measuring currently are candidates, right? We have to find the biomarker from here. So the very definition of the term biomarker means something that when measured would be indicative of the condition in our case. So from the parameters, from the large number of parameters that we are measuring right now, we would want to identify biomarkers. Now we have to assess, and we are in the process of doing so right now, whether some of the parameters we are measuring are directly indicative themselves, or they have to be morphed and massaged somehow algorithmically, right? That is the focus of the research work itself that we are doing right now. Is it possible that, out of the multi-thousands of parameters we are measuring, it may come down to a few? Highly likely. But which of those? I don't know yet. We don't know yet.
I think we have another question in the chat. Any comments on good, thoughtful talk from Vijay? Any comments on using cerebral perfusion as a basis for cognitive decline? There have been studies reported by PhysioNet, which is a large database.
So I honestly don't know much about this. One of my team members, who's a neuroimaging scientist, has mentioned perfusion. Now, from what I'm given to understand, that there are ways to, there are some of the MRI modalities that actually do observe perfusion or measure ASM. Thank you. So just there he is. Just jump in at the right time. Thank you. So we are using the ASL sequence from the MRI set that we do in order to look for that. So yes, anything that is indicative, as long as it's practically feasible, we will try to do it if we are not already doing it. So just please feel free to add anything else that you can.
Hello. Yeah,
yes,
so just here.
Go ahead.
So nothing more to add. Yes, arterial spin labeling is the cerebral perfusion method which we are using. And it has been shown that means in the stroke studies and especially the vascular insult studies, ASL has been very useful. So when you don't have PAT-related biomarkers available, which we are not conducting here in CBR, so we think that ASL and fMRI in combination may be able to predict the lacking information, which we don't have through PAT. So we have conducted a few sample studies. Around 300, 400 subjects data is available with us on ASL as well. Thank you.
Thanks, Sujas.
Any other questions? Feel free to unmute your mic and go ahead and ask.
Inder.
Yeah, hi, Srini. Hi, how are you? Thanks for the talk. Can you hear me?
Yes, I can.
Okay, great. So I mean, obviously you guys are collecting. It's an amazing kind of effort to collect this data from the cohorts that you have identified, and do this with this long-term fashion that you have. I mean, I would imagine that there's considerable benefit that can be accrued to the broader research community outside of CBR if you shared the data, right, in an effective fashion. I mean, what are your considerations in doing that? I mean, I would imagine there's obviously technical challenges, but there's also probably some policy-related issues in terms of whether you want to do it, whether you're not, whether they are what you see as the pros and cons of sharing your data with other researchers outside of your organization or outside the country, perhaps, to do analysis and inferencing.
Perfect question, Inder. Thank you. So, well, the first thing is, and I should have said this before, the objective of CBR and supported, we are actually that's the intention that Chris had, is open science. Okay, so we are not trying to hold on to the data here. Actually, that's why when I said we would like collaborators, we happily will share our data. There are no monetary issues here. But there are certainly some technical challenges and definitely some regulatory issues associated, as you would very well know in the technical challenges we can solve because, hey, the CDPG team is the one who's helping us build the platform for exactly that purpose, right? So we have made quite a bit of headway, and I see the technical challenges being addressed in the near future, not an issue. We do intend to, we have already invited researchers to submit their proposals or requests. All they have to do is write a request, write a research proposal and say, here is why I want your data. Here is a kind of analysis I want to do. Or they can say, I would like to collaborate with these people in CBR, and they can write a collaborative research proposal. They can do either of those. They will get access to the data. It just has to go through an approval process because there is some sensitivity to, eventually this is health data, right? And there is some governmental/legal sensitivity to this. It can be, I don't think there are restrictions as far as sharing in India goes, but if we are to share across borders, then there is the health ministry screening committee process that we would have to go through. And if that process is gone through cleanly, then there should not be a problem.
What is that process screening for? What are they screening
there is
for?
a committee called the Health Ministry Screening Committee.
Yeah, but
HMSC.
what are they trying to, what is that criteria that they're trying to enforce?
So this process is managed by some of our other folks in CBR here, but they basically want to make sure that obviously there are the typical things that say that, is the data adequately de-identified, if possible anonymized, is there any sensitive data here that we are exposing? We don't want to expose PII. It has to be compliant with DPDP. There are some ICMR guidelines, all of those. And is it a legitimate research question due to which we would be sharing, subject to which we would be sharing data with researchers outside India? So they have some such criteria. And there is a little bit of a process to go through. And, we are all subject to that.
Yeah, no, I understand the PII part. Obviously, clearly, you want to make sure that PII is appropriately de-identified.
Yes, absolutely.
And then
so we would cordon off PII in the first place, right? Because when the data set that is going to be used for, say, training a model or whatever needs to have no notion of PII in there. All they care about is a randomized ID that maps each cohort participant along with their visit numbers and visit dates, and then comes all the data along with it, right? But there is some socio-demo information in the form of age, gender, there is an issue about location, but what we try to do is to hide it by capturing information about their socio-demographic situation and then just showing those and try to minimize the possibility of reverse engineering from there, right? So we try to do some level of anonymization during the data collection process itself, if you will. But there is only so much you can do.
Yeah. Great. Now, what are your plans in terms of additional cohorts? And I mean, are you planning to kind of recruit more participants as you go, or are you going to just see this through, or what? I mean, what is the
No,
the
absolutely.
goals here?
So there is
Yeah.
already, there has been actually clear recognition that the two cohorts we have are grossly insufficient, right? We would start there because we needed to have the protocols for these studies identified well. But now we are in a phase where there are some people with the right kind of experience who have joined CBR, and they are trying to put together a national network of cohorts, if you will, other cohorts in India who are doing cohort studies for other purposes. But maybe we would share the protocols that we would want them to administer and measure parameters, and then they will basically add on things like cognitive assessments, gather some blood samples, and under consent, provide it to CBR. So that's the way, instead of us running more cohorts directly, we are trying to collaborate with other long-running cohorts and gather data through them.
Great. Thank you, Chini. Thank you. Thanks for the talk.
Thank you. Very, just the relevant, perfect questions. Thank you. Okay.
Yeah. Can I just ask a question? This is Dipankar.
Yes.
Okay. I actually asked it on the chat, but maybe my question was not very clear, so I thought I'll just ask it again. My question is that there is increasing concern about people using AI and ChatGPT and other interfaces and developing maybe issues concerning their mental stability. We know cases of people committed suicide and legal cases and all that. So my question was that is CBR is also looking at this space as a place of interest and started collecting any data so that some research can be done, because at some point it can be a very big problem for the Indian society, I think. With so many people.
It could be, but it requires an entirely different. I mean, from the looks of it, it would require an entirely different kind of study and data gathering effort, Dipankar. Our focus is primarily on neurodegeneration in the aging brain.
Okay, as CBR itself.
Yes.
Okay, that's the mandate. Okay.
So there are other potential cohort studies, maybe in NIMHANS or Center for Brain and Mind, that is on NCBS campus. There are other research organizations who may be engaged in those kinds of studies, but we are focused on neurodegeneration in the aging brain.
Thank you.
So we are at time. I think we can take maybe one more question if anybody wants to go ahead and ask. But if not, then I think we can go ahead and conclude. Thank you so much, Chini, for giving us this opportunity giving us this insight into CBR's work. It was a really, really insightful session.
Thank you so much, Navanil and CDPG, for giving CBR this opportunity, and I'm happy to represent us as a group. And for all of you who are in the audience, if you have any ideas, you feel you can contribute, you want to engage in a discussion, please do connect with us. and write to us. Please visit CBR's webpage, and you will see a lot of information about our cohorts and about the people we have and the kind of work we do, and you may be better informed along with that. And hopefully the content of this presentation will reinforce some things and bring up questions in your mind that may help us together solve this problem. Okay.
Great. Great. Thanks so much, Jeannie.
Thank you.
Thank you, everyone.
Bye.